Okay, so last video for Unit 3, and so this is about asymptotic comparison of sequences. Okay, so sometimes in order to solve indeterminations, just like the ones we saw in the video before, it's useful to compare how different sequences behave when n gets very large. Okay, so when n is getting closer and closer to infinity, then for instance a sub n and b sub n may be very close. Okay, so for instance we saw in the last example that the limit when n goes to infinity of 1 plus 1 over 2 plus 1 over 3 plus blah 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 plus 1 over n divided by the logarithm of n is 1. Okay? Check last video for this example, right? So this means that when n is very large, this sequence and this sequence are very similar to each other, right? So this is the rigorous definition of that. Okay, so let a sub n and b sub n be two sequences which either both diverge or both converge to 0. Okay, so we say that a sub n and b sub n are equivalent, and we denote it like this with this curly tilde, if the limit of a sub n divided by b sub n is equal to 1. Okay, so that means that if the limit of a sub n is when n goes to infinity is infinity, then b sub n is also infinity, but the division between both is 1. And a sub n is negligible compared to b sub n, and we denote it like this with this symbol, if the limit of a sub n divided by b sub n is 0. Okay, so that means that b sub n is either growing to infinity much faster than what a sub n is doing, or if it's going to 0, this is going to 0 much faster than b sub n, right? So in this case, this means that both sequences are growing to infinity at the same rate, right? We know that the logarithm of n, when n goes to infinity, which means, and this is an interesting proof of this result, that this sum, 1 plus 1 over 2 plus 1 over 3 plus 1 over n, which is called the harmonic sum, okay, goes to infinity when n goes to infinity. Okay, so this sum is, as you can think, this is the sum of an infinite number of terms that are smaller and smaller and smaller. It still go up to infinity when n gets large, right? And we will see this in next unit, which is about series, which is about infinite sums. Okay, so we'll see that in the next videos. Okay, so this is an example of equivalent sequences. For instance, a negligible sequence is, for instance, n and n squared. Well, then a sub n is negligible when compared to b sub n, right? Because the limit when n goes to infinity of n divided by n squared is 1 over n, and this limit is 0, right? Okay, so we're going to see now, so there are some equivalences that are very useful for computations, and I'm going to write them now here. This is the logarithm of 1 plus epsilon sub n is equivalent to e to the epsilon sub n minus 1, which is equivalent to the sine of epsilon sub n, which is equivalent to the tangent of epsilon sub n, which is equivalent to epsilon sub n. Okay, where epsilon sub n is a sequence such that the limit of epsilon sub n is 0. Okay, so this is a decreasing sequence. So you could take, for instance, e sub n could be 1 over n, or it could be 1 over n squared, something like that, right? Something that is going to 0. So this string of equivalences is very useful. I'm going to prove them now to you. Okay, so let's start with the first ones. So we have the limit, we've seen it before, the limit of 1 plus epsilon sub n to the 1 over epsilon sub n is e, right? Remember that? So remember we had the limit when n goes to infinity of 1 plus b sub n to the c sub n, where b sub n goes to 0 and c sub n goes to infinity, was e to the limit when n goes to infinity of b sub n times c sub n, right? Well, in this case, we have 1 over epsilon sub n goes to infinity, so it's a valid c sub n, and epsilon sub n goes to 0, which is correct. But the limit of, in this case, the limit when n goes to infinity of epsilon sub n times 1 over epsilon sub n is 1, right? So this is e to the 1 e, okay? Okay, just to remind you. So we have this. Now we take logarithms here. So we have the logarithm of this is the logarithm of this. The logarithm of the limit is the same as the limit of the logarithm. We know that. So this is the logarithm of 1 plus epsilon sub n 1 to the 1 over epsilon sub n, and equal to the logarithm of e, which is 1. And this is the limit when n goes to infinity, and because of the properties of the logarithm, the exponent goes out multiplying. So this is the logarithm of 1 plus epsilon sub n divided by epsilon sub n is 1. Okay, so that means that these two sequences are asymptotically equivalent. Okay, so this is what we're saying here. Logarithm of 1 plus epsilon sub n is asymptotically equivalent to epsilon sub n. Okay, so for instance, the logarithm of 1 plus 1 over n is asymptotically equivalent to 1 over n. Okay? Okay, next. So we have the, it's called the logarithm of 1 plus epsilon sub n. This limit of this is also 0, right? Because the limit of the logarithm is the logarithm of the limit, so this is the logarithm of the limit of 1 plus epsilon sub n when it goes to infinity, right? But the limit of this is 1, right? But the logarithm of 1 is 0. Okay, so the limit of this is 0. So we can call this sequence something like delta sub n and take it as our sequence that is going to 0. Okay, and so delta is going to 0, right? So then we have epsilon sub n, and we exponentiate both sides, so we have 1 plus epsilon sub n is delta to the delta sub n, right? And we solve for epsilon sub n, so this is e to the delta sub n minus 1. Okay, so now we have, as we had written before, 1 is the limit when n goes to infinity of the logarithm of 1 plus epsilon sub n over epsilon sub n. This is the thing that we just proved, right? But we can write now these things. This is delta sub n, right? And epsilon sub n is e to the delta sub n minus 1. Okay, so this thing is 1, so this means that e to the delta sub n minus 1 and delta sub n, where delta sub n is a sequence that is going to 0, are asymptotically equivalent. Okay, so this is the same thing. This is this, okay? So e sub n is a general or any sequence that converges to 0, okay? So in this case, this delta sub n is different than this epsilon sub n, but it doesn't matter because both of them converge to 0, okay? So this thing is valid, okay? So we can just change the name of the sequence here, okay? Okay, so now let's go for the trigonometric equivalences here, okay? So I'm going to use this plot here. Okay, so I'm gonna use this plot to show that this is true. The absolute value of the sine of x is smaller or equal than the absolute value of x, which is smaller or equal than the tangent of x. Okay, so how do we know this is true? Well, the sine, and this is true where, sorry, between minus pi over 2 and pi over 2, right? Well, this is true for the first inequality, the sine of x. You can see this is smaller than this. It's kind of obvious from the picture, right? Or you can think about it in terms of areas, right? So the area of this triangle is, let's see. Well, actually, this is going to be smaller, right? Yes, it doesn't matter. So the sine of x and this curved x is obviously greater than this. Now, this x and the tangent is not so easy to see that this is smaller than this, but you can see this with the areas, right? So the area of the sector, this is x, this is a circular sector, and the area of this is 1/2 of the angle, and the angle here is the absolute value of x. But so this is area 1, and the area of this, this is 1, and this is the tangent of x. So the area of this triangle is 1/2 times the height, okay, the absolute value, okay. And we know that it's obvious that a sub 1 is smaller than a sub 2, right? So that means that 1/2 of the absolute value of x is smaller than 1/2 of the tangent of x. So we cancel each other out, and then we have this inequality, which is what we wanted, okay? And the smaller or equal is because when you go to pi over half, these things are, or 0, their things are similar, or the same actually, okay? Okay, so we start from this inequalities, okay, that we prove using geometric arguments, okay. Now we can divide this thing by the left one by the absolute value of x. Then we have sine of x divided by the absolute value of x is smaller than 1, smaller or equal than 1, right? Now I'm going to draw the sine of x between minus pi over 2 and pi over 2. This is pi over 2, and this is minus pi over 2, okay? So this, you can see that the sine, okay, the sine of x is equal to the sine of x, right? When x is positive, the sine is positive. When x is negative, the sine is negative, right? So we can rewrite it like this: sine of x over x is greater than 0, okay? Because when both of them are negative, the quotient is positive. If x is between this minus pi over 2 and pi over 2, right? So then we can combine both inequalities and say 0 smaller equal than sine over x smaller than 1, right? Okay, so let me write it like this, okay? So now, let's say from this inequality we have absolute value of x is smaller than the tangent, but the tangent is just the absolute value of the sine divided by the cosine, right? But we can rearrange this and say that the cosine of x is smaller or equal than the sine of x divided by the absolute value of x, right? But this is smaller than 1, so now we know that the cosine is smaller than 1, which kind of we knew because that's the bound, the upper bound for the cosine. But between minus pi over 2 and pi over 2, actually the cosine, there's something like this. This is pi over 2 and minus pi over 2. This is cosine of x. So this, we can get rid of the absolute value and say that the cosine is smaller or equal than 1, right? So then we have this bond, and we knew that this is smaller than this, so we have the cosine of x smaller or equal than the sine of x over x, which is smaller or equal than 1. Okay? So let's see. So now we have again epsilon sub n, a sequence that converges to 0. Then we have the sine of epsilon sub n is smaller or equal than epsilon sub n. Okay, applying here. And then we can that this inequality implies that the sine is between these two numbers, right? Okay, if the sine of epsilon sub n is positive, then this is between smaller than this. If it's negative, it's greater than it, right? The absolute value is greater, closer to 0. Well, if now we take limits in both sides, we have the limit of this is 0, the limit of this is 0. So applying the sandwich theorem, the limit of the sine of epsilon sub n is 0, which is kind of something we knew, because the sine is this function that when it gets its argument gets closer to 0, it's also getting closer to 0, right? But bear with me. So we had the limit of the sine is 0. Now the cosine of epsilon sub n is the square root of 1 minus the sine squared of epsilon sub n, right? Now the limit of this is 0, so the limit of the cosine is 1, right? Okay. Well, if we use this fact and go here, okay, with this we are going to rewrite, instead of x, we're going to rewrite epsilon sub n. So we have epsilon sub n, epsilon sub n, epsilon sub n, right? There's this. If we take limits here, so this is the limit here, the limit, and the limit here is 1. This limit is 1. So again, using the sandwich theorem, we have that the sine of n of epsilon sub n divided by epsilon sub n, the limit of this is 1, using the sandwich theorem, which is one of the equivalences that we wanted to prove, right? So in other words, we have that the sine of epsilon sub n is equivalent to epsilon sub n, right? So this is what we want. Now finally, the limit when n goes to infinity of the tangent of epsilon sub n divided by epsilon sub n is just the limit when n goes to infinity of, and then we have the sine of epsilon sub n divided by epsilon sub n times 1 over the cosine of epsilon sub n, right? Because the tangent is sine over cosine. Now the limit of this is 1, we just proved it, and the limit of this is 1. So the limit of the tangent over the epsilon sub n is 1, so this is also equivalent to this. Okay, so this is the string of equivalences that we wanted to prove. Okay, all of these sequences are equivalent to epsilon sub n when epsilon sub n goes to 0. Okay, in other words, you can think about it as these functions are very similar to the function x when x is closer to 0. Okay, so you could plot this in software. Sorry about this. You can use any software to plot this correctly. But if you have x, okay, this function x, right? So what's the sine? The sine, I just told you, this is this function that does something like this, and then that's something like this. Okay, this is the sine of x. Well, when x is very small, right, this means that the two functions have the same behavior, right? We will see that when we get to limits of functions and Taylor approximations and whatnot later in the course. But you can think of this asymptotic equivalence as this. These two functions behave very similar to each other when their argument x is very close to 0, right? So this is for the sine. The tangent is also very similar, because the tangent, if you remember, goes something like this, does something like this, and then does something like this, and does something like this. Okay, so this is the tangent. Also, when x is very small, both things behave very similar to each other. Let's see. We have the exponential does something like this, right? Okay, this is e to the x. Well, if you subtract 1, then it does this, but then it crosses 0, okay? And then very close to 0 is very similar to x, and then it starts doing like this, okay? So let me erase this. So this was x, and this thing is e to the x minus 1, right? Okay, you can think about it, very close to x. They behave very similarly. And then finally, sorry. Well, I'm very bad at this. Okay, yes, why not? We have this, and then we have this, okay? Well, again, the logarithm of x does something like this. Okay, this is the logarithm of x. And now if you take the logarithm of 1 plus x, we have seen this. This is the same as taking shifting the function to the left. Okay, so this will go something like this, and it could grow very similar to this here, and then there's something like this. Okay, I'm very bad at plotting. So, and this is the logarithm of 1 plus x, right? So when x is very small, actually the logarithm of 1 plus x is always smaller than x, right? So you have this, they're very similar to each other, okay? So this is what it means for this sequences to be asymptotically equivalent, okay? I hope this is clear. So one exercise for you guys is to prove, using these identities, the cosine squared of x and the sine plus the sine squared of x is 1, and the formula for the cosine of the double angle is to prove this asymptotic equivalence. That is also very useful. Okay? 1 minus the cosine of epsilon squared, of epsilon sub n, is asymptotic equivalent to epsilon sub n squared over 2. Or you could also write it like this: the cosine of epsilon sub n is asymptotic equivalent to 1 minus epsilon sub n squared over 2. Okay, and if you plot this, I just told you that the cosine is like this. Okay, this is the cosine of x. Well, this means that this is very similar to, let's see, this parabola does something like this. If you know, this is 1 minus x squared. Okay, so this is 1, and in this area very close to x, this is very similar to the parabola 1 minus x squared. Okay, so very useful asymptotic equivalence. It's what we call Stirling formula. Okay, so Stirling was a mathematician that discovered this formula that is related to the factorial. Okay, so n factorial is asymptotically equivalent when n is very large to the square root of 2 pi n times n to the n times e to the minus n. Okay, so you have to memorize this by heart. Okay, you're gonna use it a lot, because in many limits we will have n factorial, and you need to use the Stirling formula to make things simpler. Okay. Okay, so how do we use this asymptotic equivalences? So suppose we have this limit, the limit when n goes to infinity of a sub n times b sub n. Okay, and we know that a sub n is asymptotically equivalent to c sub n, and b sub n is asymptotically equivalent to d sub n. Okay, well, if we have this, then we can do this limit when n goes to infinity, and then multiply and divide by c sub n, and multiply and divide by wait a minute, by d sub n, yes. So this is wait a minute, multiply and divide by d sub n, right? So then this limit is 1, this limit is 1, so the limit is the limit of c sub n times d sub n. So in products, and it's easy to see that in quotients, you will have the same rule. You can substitute a sequence by another sequence that's asymptotically equivalent to it. Okay? So just remember this because it's useful. So and as an exercise for you, use this trick to calculate this limit. Okay, so we know that the sine of epsilon sub n is asymptotically equivalent to the logarithm of 1 plus epsilon sub n, which is asymptotically equivalent to epsilon sub n. Okay? Now, you could be tricked into thinking that you could also apply this rule to differences of limits. So the limit when it goes to infinity of a sub n minus b sub n, and also a sub n is asymptotically equivalent to c sub n, and b sub n asymptotically equivalent to d sub n. So you could say, well, this is the limit of c sub n minus d sub n. Okay, you could say this. Well, this is not true. Okay, so not true. You cannot use this in differences, and I'm going to show you why with an example. So suppose we have this limit, the limit when n goes to infinity of the square root of n fourth plus n squared minus n squared minus 1. Okay? Well, you could say that, you know, n to the fourth plus n, you could take common factor n squared, n fourth, and so take it out of the root, and then you have 1 plus 1 over n squared. So this is asymptotically, the limit of this divided by n squared is 1, so this is asymptotically equivalent to n squared, right? It's easy to prove. And then you have n squared plus 1, well, this is like this. This is also asymptotically equivalent to n squared, right? If you compute the limit when n goes to infinity of n squared plus 1 over n squared, you get 1, right? So you could say this is n squared minus n squared, so you can have n squared minus n squared equals 0, okay, which is not true. Or, but see that if instead of using this equivalence here, you just have n squared minus 1, which is the original sequence, you had minus 1, you get two different limits. So this cannot be true, okay? This cannot be the case. So how do you solve this? Well, you solve this using this trick that we saw with square roots when you multiply by the sum of these two terms. So this is n squared plus n to the fourth plus n squared plus 1. And then in the numerator you have the difference of the squares. So you have n to the fourth plus n squared, and then minus, and then you have n to the fourth plus 1 plus 2n squared, right? And so then you have n to the fourth and n to the fourth cancel each other out, and then you have n squared minus n squared in the denominator. So you have minus n squared minus 1, and then you could have n squared here, as we just said, okay? And then you have n squared plus 1, right? If you divide everything by n squared, you have minus 1 over n squared, and then you have 1 plus 1 over n squared plus 1 plus 1 over n squared. So this thing is going to 0, this thing is going to 0, this thing is going to 0. So then you have minus 1 over square root of 1 plus 1, so this is minus 1 over 2. Okay? This is the limit, and not 0 or not minus 1 as we had seen. Okay? So why is this the case? Why cannot we do these things? Well, the thing is that when you are subtracting these things that is going to infinity and going to infinity, what you can see is that the leading terms, the terms that are more important, n to the fourth here and n to the fourth as well, or in this case, well, n to the square, n squared, get cancelled out, right? Because you can subtract them from each other. And then the important uh, part of the limit, so the important terms that will give us the actual value of the limit are the terms that are smaller, that are negligible in comparison with the leading terms. Okay, so that's why we cannot use this trick. But in contrast, we can actually how to say, forget about negligible terms when comparing term sequences in subtractions. So for instance, you have the limit when n goes to infinity of c sub n divided by a sub n plus b sub n, and b sub n is negligible in comparison with a sub n. Well, this, you can rewrite it like this. This is c sub n divided by a sub n times 1 plus b sub n over a sub n. Okay, but the limit of this is going to be 0, right? Because this is what negligible means. So this is just the limit when n goes to infinity of c sub n over a sub n. So the negligible sequence gets discarded, and this is what we have done here. Okay, but we have done it explicitly. But you could say, well, this is minus 1 is negligible when compared to minus n squared. So this is just the limit. Let me write it like this now. The limit of this is just the limit of minus n squared, and then you have this. In this case, 1 over n squared is negligible when comparison with 1. Okay, we know that. So this is just 1, so that we can substitute it like n squared, and then you have plus n squared, because again 1 is negligible in comparison with n squared, right? So then we have minus n squared divided by 2n squared, which is minus 1 over 2. Okay, so this is the same thing that we have done, but writing it in more explicit terms. Okay. Okay, so just one last example using this rule. Okay, so the limit, let's say, not limit. We have to show that the logarithm of 3n to the 6 minus 5n squared plus 2 is asymptotically equivalent to 6 times the logarithm of n. Okay, so now with this we have the 2 is negligible. 2 is negligible to in comparison with 5n squared, and this is negligible in comparison with 3n to the 6, right? So we can rewrite it like this. The logarithm of 3n6 minus 5n squared plus 2 is asymptotically equivalent to the logarithm of 3n to the 6, right? Now we can rewrite it like this. This is the logarithm of 3 plus the logarithm of n to the 6, but the logarithm of 3 is negligible when comparison with the logarithm of n to the 6, right? As n gets very large, this gets very, very, very important, and this is very small, right? So this is equal to, sorry, not equal, but asymptotically equivalent to the logarithm of n to the 6, which is equal to the 6 times the logarithm of n, which is what we wanted to prove. Okay, so remember this: in products and quotients, substitute equivalent sequences, and in general and in sums and differences, discard negligible terms. Okay, so the last thing I want to tell you is that this is and I think we will prove this in some of the exercises. This is a hierarchy of negligible sequences, which is very useful for calculations. Okay, so the logarithm of n to any positive number a is negligible to n to any positive number b. Okay, so that means that the logarithm is growing to infinity much slower than n to whatever, right? Well, this is negligible in comparison to any exponential function, c to the n, right? If c is greater than 1. This is smaller than n factorial, or negligible in comparison with this, and n factorial is negligible in comparison to n to the n. Okay. Well, actually, this is easy to prove if you use Stirling's formula. So you have n factorial over n to the n, and then if you use Stirling's formula, n factorial is the square root of 2 pi n times n to the n times e to the minus n divided by n to the n. Well, n to the n cancel each other out, and e to the minus n goes here, but this is just the limit when n goes to infinity of 2 pi n to the 1/2, and this is over n e to the n. But here it says that n to the b is negligible in comparison with c to the n. Well, c here, e is 1, so it's greater than 1, so we can say that n to the 1/2 is negligible in comparison to e to the n, which is what we are seeing here. So this limit is 0. Okay. So we will see some of this in the exercises, but remember this hierarchy, right? Yeah, so that's it for now and for the unit.